In this video, we are discussing the physical properties of haloalkanes and haloarenes. Haloalkanes and haloarenes are usually colorless when pure. However, iodides and bromides have a color when exposed to prolonged exposure to light. They have the volatile compounds have a sweet smell. Melting and boiling point, on the other hand, is a very interesting thing that we're going to study. So first of all, the CX bond. Now we know halogen atom is electronegative, right? So because of the electronegativity of the halogen atom, these molecules are polar in nature because of this electronegativity. Okay, and this along with the fact that the halogen adds extra weight or extra mass because that they're heavy, the intermolecular forces are stronger in these compounds compared to the ones which are just hydrocarbons without any halogen atoms. Okay, and due to this, we have two different types of forces coming into play. That is the dipole-dipole interactions as well as the van der Waals forces. We know why they both exist is because of the fact that this particular molecule is polar in nature. Now, when you have the first one is based on the size of alkyl group. When you have more number of carbon atoms, let's say we have C3, I'm going to write the chain itself. So let's say we have CH3X, CH3, CH2X. Now this is ethane, ethyl, bromoethane or chlorate. X is a halogen. And this is methane. So this particular molecule has 2 carbon atoms, whereas this one just has 1. Because of the difference in chain length, there will be a difference in terms of the van der Waals as well as the dipole interactions. And because the molecules are getting bigger, the number of electrons that are also present all gets bigger, and this in turn leads to an increase in the dipole-dipole as well as the van der Waals forces. It leads to an increase in the dipole-dipole interactions, and because of that, as we increase as the chain length increases, boiling point increases. The next one is based on the halogen atoms. Let's assume we have the same R, that is the alkyl group, Ri, RBr, RCl. And again, the R group is the same in all 3 cases. Now, the boiling point is going to be Ri is having the highest compared to RBr and then RCl. This is because there is an increase in the mass of, when the mass of the halogen atom increases, there is an increase in the magnitude of van der Waals forces. And because of this increase in the magnitude of the van der Waals forces, there is an increase in the boiling point and melting point. So R is the same alkyl group. When there is an increase in the size, there is an increase in van der Waals forces, and because of that there is an increase in boiling point and melting point. The third one is based on the branching. Now here we have bromobutane, okay, 2 bromobutane and 2 methyl 2 bromo 2 bromo 2 methyl butane. And as we see here, there is an increase in branching as we're going from left to right. This increase in branching is also leading to, if you notice over here, the boiling point is decreasing. So when the branching increases, the boiling point decreases. So boiling point of isomeric haloalkanes decreases with increase in boiling point. The next one is when you have ortho, meta and para isomers. Para isomers, due to their most symmetry, they have a high boil. So this is the boiling point and melting point. They have the highest boiling point and melting point. However, it is different for meta and ortho, and relatively speaking, they have similar boiling points. There's not a huge difference between this and this. It's pretty close comparatively speaking. But para isomers have the highest boiling point as well as melting point. The third one, the next one we're talking about is density. So density, when you have polychloro derivatives, for example, dichloromethane is a very good example. I actually work with dichloromethane, and I find it so annoying that the bottle is so heavy because of the density of the molecule itself. So that is actually pretty cool, honestly, because when you have the same volume and you try to lift two different liquids, and you can actually see that there's a difference in their masses, and that's because of that variation in density. I mean, that also implies there is a variation in their densities as well. So the density varies with three things. First of all, it increases with increase in number of carbon atoms. Now when you notice over here, you have just three carbon atoms. Oh, sorry, we don't have the example in your textbook where you have a variation with respect to number of carbon atoms, but as such density increases with increase in number of carbon atoms. The next one is when you have a same molecule with different halogen atoms, you notice that as the mass of the halogen atom increases, the density is also increasing. So chlorine C3H7Cl has the least density compared to C3H7I, which has the highest over here. The next one is as the number of carbon atoms increases, there is also going to be an increase in the as the number of halogen atoms increases, there's also an increase in the density. And if you notice over here, you have 1.336 for CH2Cl2, whereas for CHCl3 it's 1.489, and for CCl4, carbon tetrachloride, it is 1.595. And CHCl3, I believe, is chloroform, which is also pretty dense. And this is dichloromethane, CH2Cl2. And to put things in perspective, the density of water is approximately 1. The next and the last one that we're going to be talking about is the solubility. Now, so when you have, so let's assume you have a haloalkane in this, okay, and I'm going to call it Rx. Excuse me. So Rx, and so there are many molecules of Rx in this liquid. Now this Rx and another Rx, like they will have a particular type of interaction between these two molecules. Now let's assume we have water over here, and obviously between two water molecules you have something called a hydrogen bond. Now when we mix these two, we get this beaker filled with Rx, H2O, H2O, Rx. Now what needs to happen is, for this Rx to get dissolved in water, it needs to break this interaction. Okay, this interaction has to be broken, and the hydrogen bond between two water molecules also has to break. And there has to be a new interaction formed between the Rx and water. And because this is weaker than this or this, the haloalkanes and haloarenes do not dissolve in water. However, if hypothetically if this had been an organic molecule, like an organic solvent, then it would have dissolved, because the interaction between two haloalkanes will be similar. That interaction's energy will be similar to that of the solvent and the haloalkane itself. And that's it. So let's start with melting and boiling points. When you have, first of all, they're polar in nature, and because they're polar in nature, you have both dipole interactions as well as van der Waals forces. When there is an increase in the size due to an increase in the number of electrons, there is an increase in the boiling point as well. Next, based on the halogen atoms, with the increase in the number of size, there is an increase in the number of mass, and because of that you have an increase in the increase in the boiling point. Because of that, you have chlorine less iodine more than bromine, which is more than chlorine, with the same R group attached to it. One more important thing I'd like to add: when you have more substituted ones, which we will discuss, there is obviously going to be a change in the boiling point. So when you have the number of halogen atoms increasing, there is going to be an increase in the boiling point. The third one was based on branching of the alkyl group. When there is an increase in the branch of alkyl group, there is a decrease in the boiling point. And I would suggest you go back to class 11 where you learnt about the boiling and melting points of alkanes, alkenes and alkynes. There was a very good explanation as to why the branching changes the boiling point and melting point, and I will put the link in the description below as well as the banner above. The next one is when you have para, ortho and meta isomers. Para, because of its highest amount of symmetry, has a higher boiling point and melting point compared to ortho and meta. Next is density. Density varies with respect to the number of carbon atoms. It also varies with respect to the presence of chlorine, bromine or iodine. Chlorine with the least, and it's obvious as the mass of the molecule, the atom is increasing, there is an increase in the density as well. And also density increases with increase in number of halogen atoms attached to the carbon. So here you have dichloromethane here, and which has 1.336, chloroform which is 1.489, and carbon tetrachloride which is 1.595. So the density is increasing with increase in number of halogen atoms. The last one is solubility. Basically, two haloalkanes, when they are in the solution, or like when they're liquids as such, there's going to be some amount of interaction between the two haloalkane molecules. And as we know, water also has hydrogen bond as the interaction between those two. So for a haloalkane to get dissolved into water, this interaction should break, as well as this interaction should also break. The issue is that this is not as strong as this or this. And because of that, the haloalkanes are not particularly soluble in water. However, when you have an organic solvent, they tend to get dissolved, and that's because the interaction formed between the haloalkane and that particular solvent molecule is as strong or almost as strong as the interaction between two haloalkanes as well. So with that, we're done with the physical properties. In the next one, we are going to be discussing the chemical properties of haloalkanes and haloarenes. Oh no, but before that, we will be learning about the in-text question given in your textbook.